Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last class I started talking about carbon ion and I talked about the generation of carbon ion and then different reactivity. In the today's class I am going to focus on different type of rearrangement reaction using carbon ion. So I am going to talk about the 1,2 shift of carbon ion, and then I am going to talk about various different rearrangement reactions starting from benzylic acid rearrangement, then very important the Favorsky rearrangement, the Coesi-Favorsky rearrangement, then the Ramberg-Buckland rearrangement. I am going to talk about the Becker-Venkat-Raman and then Pine rearrangement, and I am going to talk about some of the example as well. Okay. So, there will be example and mechanism. So, first thing I am going to talk about that why the 1,2 shift of carbon ions are less favorable. So, if you remember, I think during carbocation when I was talking about 1,2 shift after the Wagner-Marvin rearrangement, I started talking about that why in case of carbocation we know that the 1,2 shift is very much favorable, but in case of carbon ion it is not favorable, because what is happening here, once you go for a 1,2 shift, then if you go through this tangent state, and we closely try to look about this tangent state. In the tangent state, if you see, there is some sort of a cyclopropane ring, cyclopropene, and there is a carbon ion. So what is happening here? This is actually generating a anti-aromatic tangent state. As it is going through anti-aromatic tangent states, that's why this is less favorable. Okay. So that is why we generally don't see much this type alkyl 1,2 shift, but instead of this group, if you have a phenyl group here, suppose you have a phenyl group here, then if you have a phenyl group, then the things will be little different. In case of phenyl group, there will be a 1,2 aryl shift. So what is happening? Why in case of phenyl it is so different? Once you have a phenyl group, what is happening? This lithium which is forming here, through the metal halogen exchange of this carbon chlorine bond, now this anion can attack here, this anion which is going to form here going to attack to form this corresponding carbon ion here. Now you can see this carbon ion is getting stabilized through the resonance. You can able to draw the different resonance structure here, and then you can draw the next one going to go here, and then what is going to happen at the end of the day, it is going to break this bond and going to form this carbon ion, which is again a dibenzylic carbon ion. So that is why this carbon ion is getting very much stabilized here. That is why this 1,2 aryl shift is happening. So this aryl group now migrating from this position to this position at the end, and then it is finally trapping with CO2 to form this product. So we can give you some evidence of this, that is it happening or is not. So now what is the first thing what is happening from this compound, the metal halogen exchange can generate this corresponding carbon ion. I think there will be a phenyl group which was missing here. So there will be phenyl group here, and now once this carbon ion formation is happening, this can attack here, as I said before, that is going to attack here, and which will generate this carbon ion here. Again I said this is a benzylic carbon ion getting stability, so it can able to react with the CO2 to form this corresponding product, and this compound, the last one, can be isolated, and it was confirmed through the XRD structure. So now this is kind of giving a clear evidence of this 1,2 aryl shift. Now I am going to talk about a benzylic acid rearrangement. So it is giving benzyl to benzylic acid in presence of base. So what is happening here in this reaction, the base actually not able to find any proton to abstract, there is 2 phenyl group. That is why it is attacking to the carbonyl group here to formation of this corresponding intermediate, and now this O- is coming back, allowing this 1,2 migration of this phenyl group, okay, and that is forming this compound, which is this O- is abstracting this hydrogen, which is acidic hydrogen, which is which can be abstracted to generate this type of anion species, which can get finally take proton to get to the corresponding OH. Okay. So now we are going to learn about the different aspect of this benzylic acid rearrangement. One of the thing is that if you have some sort of a molecule where you have a intramolecular 1,2 dicarbonyl compounds. Now what is going to happen in case of NaOH? Again the NaOH is going to attack here, and now this phenyl group internally going to get migrated. So once it is going to attack here OH, it will be O minus, and then what is going to happen, this will come back and this phenyl will migrate. That will give this product. It can not only happen for phenyl, it can happen if you have a 2-furan also. From furyl it can convert to furylic acid. So at the end what is happening, you are forming a carboxylic acid and a OH. It can happen also in case of aliphatic ketones, aliphatic 1,2 diketones, but the yield will be less for sure, because there will be some other reaction as I mentioned. Then if you have some alpha proton of this carbonyl compound, then this alpha proton can be abstracted, it can go for condensation and some other transformations. But of course it is also going to form this particular product. So here what is happening in this reaction, what we are observing in this example and this example, that there is a ring contraction happening. So if you want to do a ring contraction, one of the options is you can make a dicarbonyl, treat with NaOH, it will be able to make to the corresponding carboxylic acid. And this can happen also in this example. Now the question comes that if you have a unsymmetrical aryl group, like you have a phenyl one side, you have paramethyl phenyl other side. Now what is going to happen? Now the problem is the first step, when the base is attacking, it is going to find the carbon of the carbonyl of which is more electron deficient, because you have the plus I effect of this methyl, the OH must choose to attack to this carbonyl group, which allows this phenyl to migrate to get to this corresponding product. There are example, if you have a phenyl versus instead of electron donating group, now you have a electron withdrawing group like a nitro group attached. What will happen? Now again, as the nitro group is electron pooling, is taking the electron density from this carbonyl group, making this carbonyl more electron deficient, and the OH minus can attack here on this particular carbonyl. Then the nitro group, this nitrophenyl can participate in 1,2 migration here, and then it is going to go to the corresponding product. Now we are going to move to the Favorsky rearrangement. So what we have learned in benzylic acid, that there will be these 1,2 dicarbonyl compounds to this corresponding product. Okay. So here what is happening, we are breaking this carbon-carbon oxygen bond through attacking of the OH minus. But here what we are going to talk about, we are going to talk about breaking of carbon halogen bond, okay, which from the ketones it will end up giving you corresponding esters, and this X will be replaced by R2. So here is an example here. So this is an example from cyclohexanone. You can able to make this corresponding alpha bromocyclohexanone using bromine and acetic acid. Now once these compounds are treated with sodium methoxide, what is going to happen, if this is my alpha position, this is my alpha dashed position, it is going to abstract this proton from here, go for SN2 type of displacement to remove this bromine, and which is happening here. It will form some sort of a cyclopropanone intermediate, which you can see here. It is forming this cyclopropanone intermediate. Now the OMe minus can attack here in the carbonyl group, and then it can open up and cleave up this carbon-carbon bond here to form this product. Now of course, if you said that if you want something like some other thing instead of the OMe, based on whatever base you choose, you end up that type of product, that type of esters actually. Now the question comes, if you start with two different starting material where you have this type of alpha chloro compounds, or you have this chlorine which is next to the phenyl ring. So starting from this compound 1 or compound 2, you still end up getting the same product after Favorsky rearrangement. So the question is, what is happening? Now if you try to think about the mechanism of it, now here also there is a alpha and alpha dash position. So it is going to abstract this proton, and then from the anion going to get attacked here from this type of intermediate. If it is starting from this compound, also going to happen very similar thing, it can abstract this proton here from the negative charge, attack here, okay, from this same intermediate. Because it is forming same intermediate, now once the OMe minus is attacking, it is going to the same product. There is an example in the natural product synthesis, starting from this particular compound. Now if you see about this compound, they already have a alpha chloro here, there is alpha chloro carbonyl group. Now there is this alpha dashed position, which where the proton is getting abstracted, it is going to attack here, to get rid of the chlorine, and then in this cyclopropanol intermediate, the OMe minus is going to attack here, and then finally it is going to open up this bond to form this corresponding open up this bond to form this corresponding product. Again, what is going to happen if you have a dibromo here? Suppose you have a species, so you have a alpha beta unsaturated compound is first getting 2 bromine here. Now you have a alpha here and you have a beta position, both have a bromine, and you have a carbonyl group. So first thing going to happen, there you have a alpha dashed position which will be getting abstracted by where the proton is getting abstracted. Now it is going to attack here to get rid of this bromine to form this type of intermediate species. Here the OMe minus is going to get attacked. Now this is going to cleave this bond, as I said, it is going to cleave. Instead of forming anion, it is going to get rid of this corresponding bromine to form this corresponding alpha beta unsaturated compounds. And then I am going to talk about another example of cohesive Febrovsky rearrangement. So what is happening in case of Febrovsky? We have learned that there has to be alpha dashed hydrogen atom which is getting abstracted. Now the question comes that if you have a scenario here where you have a corresponding carbonyl group, you have this alpha chloro, but you do not have this alpha dashed proton, which is the first step to abstraction by the base, and then it is going to get rid of the chlorine. So what is going to happen? Now this will kind of have a very thing similar, it will have a mixture of this benzyl acid rearrangement. That means we have learned that the base can now attack to the carbonyl group. So the base can come and attack to the carbonyl group here, okay, to form the O minus, which will come back, and then this phenyl group going to get migrate and get rid of this chlorine to generate this type of carboxylic acid compound. Okay. If you have instead of this compound cyclohexyl, if you have this N-methyl, then this compound is used as a painkiller which was synthesized using this cohesive Febrovsky in rearrangement reaction. So what is happening, again I told you in the previous slide that this base is going to attack very similar to the benzylic acid. Their first step is attacking the carbonyl group, formation of the O minus. Now as you have a alpha chloro group here, it will participate into this 1,2 migration, the 1,2 phenyl. So it is going to happen to form this corresponding product. Now the question comes that sometime we also see that if you use a semi-pinnacle rearrangement also happens, where if you have a OH and OTS, because here we can able to make them from the corresponding alcohol using tosyl chloride and pyridine. I already talked about this type of reaction. Now if you treat with base, it is going to form this O minus here. Now you can see here, once it is forming O minus, now this sigma bond actually aligning the anti-periplanar. So this sigma star is going to get electron density from this sigma. So and this is actually anti-periplanar to this bond, so that will allow this bond to migrate from here, from this carbon to this carbon, and this is going to form this product as a major product, okay, which you can see here in the mechanism. Now there is another example here. You can see there is a carbonyl group here and there is a carbon bromine bond. As soon as this carbonyl group was reduced using lithium aluminum hydride to make a corresponding O minus, this is allowing this bond to be cleaved, okay, because now what is happening, as I said you, that there will be a sigma star of this carbon bromine bond, where this sigma bond is giving electron density. So now there is a ring contraction happening here. What you have seen here, this group will finally form a aldehyde, and instead of 6 member it will form a 5 member ring, okay. And then there is another example here which you can see there. In this case also you have a 5 member ring at the beginning. So I am trying to show you that 5 member ring here. Now what is going to happen? You first there is a reduction to form the O minus, then very similar to this there will be a 1,2 shift going to happen which will convert this 5 member to the 4 member ring. Now it will become a 4 member ring with a corresponding aldehyde, okay, which you have seen in the very clearly given in this mechanism that this particular bond is going to again participate in the shift to giving electron density in the sigma star to form this product. Another example here that you have a 2 different alcohol. Now here you can see there is one is tertiary, another is a secondary. So if you use a methyl chloride pyridine, we have learned before also, it is going to only form mesylate to the less hindered alcohol. Now once this is getting methylated now, and this proton is getting this OH is getting so this hydrogen is getting abstracted to make a O minus. Now this is allowing a 1 to shift. What is happening here? This bond actually now ready to give electron density to the sigma star orbital here. So this sigma to sigma star donation is happening, it will allowing to cleave this bond and get rid of this OMS group, which is happening here. And after the cleavage of this bond, you will see there will be a formation of olefin, and then this will be becoming this O minus finally giving. So there will be positive charge going to form here, which is going to O minus can give electron density to form this corresponding carbon group here. So now we are going to move to another important rearrangement reaction called Ramberg-Buckland rearrangement reaction. So this is a base catalyzed rearrangement of alpha halosulfone to produce alkenes via episulfone intermediate. So previously in the Favorsky, if you remember, I was talking about alpha bromocarbonyl compound, but here I am talking about alpha bromosulfone. So now once you treat with base, what is happening? In case of Favorsky rearrangement, we have seen that there will be a ring contraction going to happen, and then also formation of ester. Here what is happening? We have formation of E and Z olefin. Okay, so starting from a alpha bromosulfone is formation of E and Z olefin. Now we are going to find out which will be major and which one will be minor. But after the original discovery, the Meyer group has a a modified condition where they find out that you can start with this sulfone. You don't have to take this brominated at the beginning. Treat with KOH and CCl4. So that will allow to generate the corresponding starting material, which is going to participate in the Ramberg-Buckland rearrangement. Okay, so we are going to talk about some of this E versus G selectivity. So what is happening? The first step is again the abstraction of this proton by by base to generate a carbon ion. Now this anion can attack here, very similar to the we have seen in case of the Favorsky, to formation of this episulfone intermediate. Now what is happening? Once you are generating a carbon ion here, okay. Now if you have a stabilizing group, if R2 become a stabilizing group here, then what is happening? Then there is a chance of epimerization. So now you can, instead of making the syn episulfone, you will make an anti-episulfone as well. So that means these two group will be anti, not syn. So now what is happening from these two scenario, after the exclusion of sulfur dioxide, it can forms this olefin. So in general, the Z olefin is the always a major product. But what is happening if there is a strong base used for this reaction? Suppose if you use a potassium tarbutoside with tarbutanol, then the E is giving as a major product. In general, with KOH condition, this is the major product, which is the Z olefin, because if in the corresponding episulfone, if you seen that if both the methyl in the same side, then after the SO2 elimination, they will form the Z. But if it is there in the anti, then only they will form the E. So means what is happening? Once the base is becoming very strong, then the anti product will be a major product. We are going to see that in case of phenyl, when there will be two phenyl group here, so this will be a phenyl instead of methyl. So once you have a phenyl here and a phenyl here instead of methyl, what is going to happen? It actually means this compound, then using the KOH you can end up making to the trans-stilbene. So what is happening? Why it is forming 100% E? Because again, what is in the corresponding transition state when it is forming the episulfone. Now if you talk about this particular stage, here because this phenyl ring getting stabilized, this carbon ion, as I said before, that carbon ion in the phenyl ring getting stabilized, now this center is getting epimerized and it is going to a episulfone which is more stabilized, because the trans will be a more stabilized episulfone intermediate, which will finally after the SO2 forming the trans-stilbene. Okay. So now I am going to talk about the Becker-Venkataraman rearrangement. That is another important rearrangement of. So this is also a base induced rearrangement of 2-acetoxy acetophenone to 1,3-diketones. Again, so what is happening? It is a rearrangement of the 2-acetoxy acetophenone. Now once in presence of base, this proton is getting abstracted, which is going to form a enol, which is going to come back and take this group here, the COR1 group, which is getting transferred. And now after this stage, what is happening? This O minus is coming back and cleaving this carbon oxygen bond, forming of this corresponding phenol. So what is happening at the end? It is taking a proton to go to the phenol, and this 1,3 dicarbonyl compounds. So now if you in this reaction, after this happening, if there is a treated with H2SO4, then it end up forming substituted chromones. So now starting from this this compound, it can end up making the substituted chromones. Again the first step is formation of this enol, which is attacking this center again, and then it is getting transferred here, and now again the cleavage of this, so this O minus comes back and cleavage of this carbon oxygen bond, formation of this intermediate which getting protonated. But now once you have more acid in this medium, stronger acid, this can protonate this corresponding carbonyl group here. Now this oxygen can attack through this lone pair, and then after elimination of the water, it can form chromones. The another important rearrangement is the SN-Moser sulfide contraction. So what is SN-Moser sulfide contraction? We are going to learn that this is a synthesis of 1,3 dicarbonyl compound, that is your product, and what is your starting material? Again you have a alpha bromocarbonyl compounds and you have a thioester. So starting from a thioester and alpha beta and a alpha bromocarbonyl compound, in presence of a base is converting to a, and also using a phosphine. In using lithium bromide, using ACN as solvent at 70 degrees is forming 1,3 dicarbonyl compound. What is happening? First thing is you can see sulfurs are very good nucleophile. You are going to attack to this carbon bromine bond through SN2 to form this compound. Then in presence of base, what is going to happen? Base, it will going to form a enol, and it is going to come back and then going to attack here to the, this carbonyl to form this type of intermediate. Now the phosphorus going to come to the system, phosphorus going to react here, and after that it will going to get rid of this corresponding PR3 double bond S compound, and it is getting protonation to this corresponding compound. Now what is going to happen? Previously we have seen the formation of the 1,3 dicarbonyl compound, but if you start with the thioamide instead of thioester, if you start with thioamide, then it end up forming a alpha beta unsaturated ester. Again you have to use this alpha bromo ester or alpha bromo carbonyl compound here. Again there is another example also given here. If you have a alpha, so this bromo is next to alpha to the carbonyl, alpha to the ester, which can also form these alpha beta unsaturated compounds. So now we try to understand the the mechanism of this reaction, what is happening. Again the sulfur is attacking first through a SN2 to form this corresponding intermediate species. Now what is happening again, so this proton is getting abstracted in presence of a base to form a enolate. That enolate is coming back and attacking here, and then it is forming this type of thioarene intermediate. This thioarene intermediate is getting open to form this type of imine thiolate. Now what is happening, the PR3 is getting whatever the phosphines are there attacking here, forming this type of tangent state, and then this type of intermediate species which can now able to form this phosphorus sulfur bond, and after that they able to get rid of this part, phosphorus and sulfur, forming a double bond very similar to the Wittig olefination to form this corresponding product. The other rearrangement I am going to talk about is the pine rearrangement here. So in the pine rearrangement, what is happening? We are forming, so it is a base induced intramolecular rearrangement where 2,3 epoxy alcohol is converted. So it is actually a displacement of 2,3 epoxy alcohol is known as a pine rearrangement. So what you are going to see, that the 2,3 epoxy alcohol is converted into the 1,3 epoxy alcohol. Mostly you are going to see there, the 2,3 epoxy alcohol is converted to the 1,3 epoxy alcohol in presence of base. So it is so what is happening in presence of base, this OH minus this proton is getting abstracted, which is now attacking through a SN2 reaction. So there will be a stereo inversion happening, and then opening up this another epoxide in the molecule. I am showing here in presence of base, abstraction of this proton, then attacking here, and so this is going to open through a 3-exo trait. According to the Baldwin's rule, this will be a favorable one, and then it is going to form the product. Now if you have a scenario here that if you start with these particular compounds and if you treat with this particular base, what is going to happen? So you have this terbutyl, so if you have a terbutyl S minus in place of NaOH, now you have a terbutyl thiol and NaOH. So now what is going to happen? So here first thing is, again as you see, there is a base going to abstract this oxygen proton, making a O minus, and now once abstracting the proton, first thing is the stereo inversion. So you should be carefully looking into this. Once it is doing here, we are making this epoxide. So first thing is a first SN2 happening. Okay. Next there is this oxygen which is forming a O minus, which is getting to the proton forming this particular compound. But as you see that you have this terbutyl thiol which is getting deprotonated in place of base. So now this particular thiol is also attacking here to the unhindered position of the epoxide. Okay. Once it is opening up, it is forming these particular compounds. So now you have a kind of a diol here with this terbutyl thiol group attached to it, and if you take a proton, it is getting protonated to form this product. So in the today's class, what we have learned about the first, we have started with the carbon ion. We have learned about the the 1,2 shift. We have learned why the 1,2 shifts are not favorable at the beginning if you have alkyl. Then you talk about if you have a phenyl there, then the 1,2 shift is happening for the phenyl group is getting the 1,2 shift, because the corresponding the anion which is generating the dibenzylic carbon ion is getting very much stabilized through the resonance. And then we talk about the various different rearrangement reaction. We started with the benzylic acid rearrangement, where you have seen starting from benzyl we are getting benzylic acid. So the base is attacking to the carbonyl, then there will be a 1,2 shift to get to the corresponding product. We have learned about the Febrovsky rearrangement, that if you have alpha bromocarbonyl compound and if there is a alpha dashed hydrogen, it can be abstracted with a base, get rid of the bromine, and then that ketone can be attacked with a corresponding base and opening up of this cyclopropanone intermediate to the corresponding esters. We have learned about the cohesive Febrovsky rearrangement, where you do not have a alpha dash hydrogen, so it is attacking of the oxygen followed by the 1,2 shift happening to get rid of the chlorine. Then we have talked about the Ramberg Buckland rearrangement. We talk about the Becker-Vankerman rearrangement. So we talk about the formation of the phenol and the 1,3-dicarbonyl compounds. We talk about the SN-Moser sulfide contraction. There also we talk about how this reaction is very important to formation of this product. We talk about the Pine rearrangement, and again the reference will be the very similar things. You can go through the Claydens and the Carey-Sandberg and the Smith of organic chemistry and the modern physical chemistry by Dougherty. And if you have any doubt or any questions, please feel free to reach me. And thank you all for the coming to the class, and I am going to look forward to see you guys in the next class.